Thank you. Thank you to the organizers for inviting me a couple years ago, and I'm thankful that they decided to reorganize this now. That's great. Eventually, we'll be living in the present instead of in the past, I hope. So, okay, so I've been working on generalized Kahler again more recently with a student of mine who's graduating imminently in the next couple of weeks, whose name is Yuzhong Jiang. And also a postdoc, Daniel Alvarez. And this work is based on kind of trying to complete a long-term project of understanding generalized Kahler geometry, understanding somehow what the structure of it is. And it's the culmination of many years of work, but not just by us, by many people, especially in the physics literature, some of whom are in the audience. So it'll be based on a paper of mine with Francis Bischoff, a paper of mine with Francis Bischoff and Maxim Zabzin, and also it's based on some previous works involving Zabzin, Rocek, Hull, Chris Hull, who's in the audience, and Richard van Unge, and Ulf Lindström. And so little by little, we've been trying to look at the physics literature to try to figure out what the physicists were finding in this geometry, and little by little, we get a bigger understanding. And there's something quite interesting that we found recently that I thought would be good to expose here. So, what is generalized Kahler geometry? So this was discovered in 1984 by Gates, Hull, and Rocek. And what they said was that we should consider a manifold with a Riemannian metric and a complex and two complex structures, I plus and I minus. And both of these complex structures are compatible with this Riemannian metric. And that's the unusual thing about it. Martin told me that it's like a schizophrenic Kahler manifold where it doesn't know which complex structure to use. And in a way, this is coming as the target, this is the target of a 2D sigma model with n equals 2, 2 supersymmetry. And the idea is supposed to be that as the string propagates in time, the vibrations of the string can move either left along the circle or right along the circle. And depending on which part of the spectrum we're talking about, depending on what part of the field space we're talking about, this part of the field space is going to see a different complex structure than the other part of the field space. So that's what he meant by that. Okay, and these are supposed to satisfy a certain condition, which is that if I take what would normally be the Kahler form, which is G composed with the complex structure, these are no longer closed. So these are not closed. But instead, they satisfy the following condition, that dc of omega, what's the dc of omega, is equal to 0. And if we call this quantity, this 3-form H, oh, by the way, this operator, this is I del bar minus del. So this is the other real operator that you can build when you have a complex structure. You can take the d bar operator and subtract the del operator and then multiply by I. And so this will be an operator just like the exterior derivative that takes a 2 form into a 3 form. So this is a 3 form. A real 3 form. Okay? And the 3 form should make you think of Gerbes. Okay, so anyway, this 3 form, the 3 form that you get from the plus side and the 3 form that you get from the minus side should be opposite in sign. Okay? And dH is equal to 0. Okay, so that's what they discovered. They discovered that unlike, they basically generalized Kahler geometry, where in Kahler geometry you could just take these two to be the same. And then in that case, this is closed, and so the 3 form is 0. Now, right. Just an interesting comment about this is that this, if I just combine this with the definition of H, you see that you get d dc omega is equal to 0. So omega is not closed, but it's what's called pluriclosed. This is called pluriclosed. Okay, and over the long period of time since 1984, we've discovered many examples of this type of geometry. There's tons of them. They're very plentiful, just like Kahler manifolds. Nowadays they're easy to construct, and we have tons and tons of examples. They exist, for example, on any semi-simple even-dimensional Lie group, like, for example, SU3. If you think of the group manifold SU3, that's an 8-dimensional compact manifold, and it has one of these. But that's the case for any even-dimensional semi-simple Lie group. But not only that, we also have interesting complex manifolds. For example, there's lots of interesting complex surfaces, which are 4 manifolds, that are Kahler, but you can deform the Kahler structure into one of these so that the 2 complex structures are different. Or you could take a 4-dimensional manifold, which is complex but not Kahler. So it's a complex manifold that is not Kahler, but it can have one of these. So we're, at this point we've got a lot of them. On coadjoint orbits, coadjoint orbits of yes, yes, there are examples there. There's actually some of those are hyperkähler. If you take a complex group, some of them are hyperkähler, and anytime you have a hyperkähler, it will obviously it will give you something like this, where you could take I and J. But the interesting thing is that when you take a hyperkähler manifold, then what you can do is you can deform the hyperkähler manifold to break the hyperkähler structure and remain only I and J compatible with G. So you can modify G in such a way that, anyway, so the answer is yes. There's tons of examples of these things. Okay, but so we wanted to go deeper into their study, and the main contribution that I made to this subject was to realize that this is equivalent to the following geometric structure. Okay, so you could take T plus T star of the manifold. This is equipped with an inner product of split signature, and it's equipped with a bracket which is called the courant bracket. And as a result, this thing is called a courant algebroid. And the point is that the bracket can be twisted by a 3-form H, and so that's what we'll do. So So the first thing that we have, so there's going to be a bunch of data here, but the first piece of data is that we're going to take this canonical bundle with this canonical inner product and this canonical bracket, canonical except for the fact that it needs a 3-form to be defined, and we have a 3-form, so we're going to use the 3-form to define the courant algebroid. So this is a replacement for the tangent bundle of M, in the sense that we're going to do generalized geometry in the sense that we're going to do geometry on this bundle rather than on the tangent bundle. I'm sure that most of you are well aware of this by now. Okay, and then in addition to this, we're going to need some complex structures. So we're going to have JA and JB, a pair of integrable complex structures on this bundle, which commute. So JA, JB is equal to 0. And then there's a positive definiteness condition, which is that if we combine them together, we get a positive definite inner product on T plus T star. You know, this one has signature dim M, dim M. This has a certain split signature, but when you put these generalized complex structures together and you put them in here, then you get something that's positive definite. So this is what we call a generalized metric. Okay, and you could define it like that. You could say we have a generalized metric. Okay. Okay, so that's what this. So it turns out that this is equivalent, and the formula for this basically is the following. You just combine these complex structures and make a matrix out of it like this, and you could change the sign. Okay, so what this means is that if I take the data on the top board, this classical geometric data, and if I plug it into this matrix, then this thing will act on T plus T star. And the remarkable thing is that these two operators will commute and they will square to -1, and we get a completely different interpretation of the same geometry. Okay, so that's an old story that started me off in this subject. Okay, so the main, so there's many things that you can determine about this geometry once you have understood it in this fashion. Okay, so once you've understood that this geometry is nothing but a pair of commuting, basically a pair of commuting S1 actions, if you think about it, these are complex structures, and so they are infinitesimal generators for S1 actions, right? So what you're saying is that there's two commuting S1 actions on your space. And so then it becomes a lot easier to analyze this geometry, and we use this to construct many examples, a lot of new examples, and so on. But the thing that I want to use today is something structural about the geometry that we learned from this. The easiest way to describe what that is to look here at this part of the matrix. This part of the matrix is a map from T star to T. So in JA and JB, we find QA, which is just the top right corner, which is a bivector field, and we also have QB, which is also a bivector field. And these are Poisson structures. So, right, and okay, and furthermore, so what I'm going to get from this is that on the manifold, we basically have two Poisson structures, and these Poisson structures have symplectic leaves. Okay, so they determine two foliations on the manifold. So one of them has a leaf like this, which is like the A foliation, and the other one has a leaf like this, let's say. And so we have two foliations, one by QA and one by QB. So we have a pair of transverse singular foliations on M. This means that the dimension of these leaves, as is, Poisson structures, that's how they are. The dimension is not constant. However, through every point, there will be a smooth leaf of B and a smooth leaf of A, and those two submanifolds will be transverse in the sense that they will sum to the full tangent space. Okay, so this is what you get. And then once you have two transverse foliations, you can obviously take their intersection, and that will give you another foliation. So this foliation by intersections, this is a third foliation, a third singular foliation. And this is associated to what's called the Hitchin Poisson structure, which can be written in this way. Notice that this one can be written as I plus minus I minus G inverse, and this one can be written as I plus I minus G inverse. And this one is written as I plus commutator I minus G inverse. And all three of these are Poisson structures. Why do I what? What about it? What about the Jacobi identity? Oh, integrable complex structures. So there's an integrability condition here, which means that it has to be, this has to be involutive for this bracket. No. They have certain laws, but it's not simply that. It's not, there's an interesting law that Zabzin also understood early on between these two, but they're not compatible in the simple sense. So anyway, we have three Poisson structures here, which are making the geometry quite rich. And okay, and so I would like to say a little bit more about these. Okay. So now, okay, so in order to kind of go deeper, what we need to do is remember how we analyze Kahler geometry. So when we're talking about Kahler geometry, it's very useful, Kahler manifolds, right? We think of them, you could think of it this way. I is G-compatible complex structure, and omega is closed. So, and the way that we like to think about Kahler geometry is that we like to break it up into two steps. The first step being the definition of a complex manifold. And then on top of this complex manifold, we have the cohomology class of omega, which we could think of as being in H1 of omega 1 on X. This is the Kahler class. Okay. And then within this class, we have an infinite dimensional space of Kahler metrics of the form omega plus I d d bar of a function. Okay, so we like to break it up into stages where we have a complex manifold at the base level, and then we have the potential of choosing a Kahler class. This Kahler class has a holomorphic interpretation. So we remain inside complex geometry, which is, everyone knows complex geometry is the best kind of geometry. Everything's perfect, it all works well. And then we break out of that for the last piece of information, which is the choice of the representative in this class, the choice of the Kahler metric, and that's like an infinite dimensional thing. Okay. And so what we're looking for is something analogous to this. What we would like to have is, we'd like to understand what is the holomorphic substructure of a generalized Kahler manifold. Now, of course, Gateshall-Rocek told us something about it because they told us that there are two complex structures. So there's two complex manifolds. But what else is there, right? These other conditions, they need to be interpreted in a holomorphic way. So the goal of what I'm trying to tell you today is that we want a holomorphic interpretation of the geometry, okay, up to the metric. I just mean that at some point we're going to have to break free from holomorphic geometry because we know that the metric is a C infinity degree of freedom, which is infinite dimensional. But at least there should be some holomorphic structure there, and that's what I want to tell you about. So any questions about the concept of?
So did you mean to say that the Hitchin foliation up here is the intersection of the A and B foliation?
Yes. Okay, now okay, so let me erase more. Okay, so it turns out that what Hitchin observed about this QH, so wait, let me not screw up this board. I'll just say that QH is holomorphic. This was observed by Hitchin. So in other words, if I take I plus Q plus I Q, this will give me a holomorphic section of wedge 2 T10 for I plus. And this is holomorphic Poisson structure. And then if I do I minus, I get another holomorphic Poisson structure. So this means that, that on these two complex manifolds, the I plus complex manifold and the I minus complex manifold, and by the way, one of the things that we learned was that I plus and I minus, they do not have to be isomorphic as complex manifolds. Even though they coexist on the same smooth manifold, they could be non-isomorphic as complex manifolds. Like, for example, you could have P1 cross P1, or you could have the second Hertzebruch surface. Both of these have the topology of S2 cross S2, but they're not the same complex manifold. This could be I plus, this could be I minus, okay? So, but anyway, the point is that on these two complex manifolds, we have, at least we know that we have, from Hitchin, a holomorphic Poisson structure. So they're holomorphic Poisson manifolds. Okay, and this, when this was understood, this created a lot of excitement because it means that this type of geometry knows about Poisson geometry, this generalized Kahler, it knows about holomorphic Poisson, and we know that holomorphic Poisson is moving into the non-commutative. So holomorphic Poisson manifolds have something to do with non-commutative deformations of complex manifolds, and this generalized Kahler knows something about that. And in my recent work, I've been really pushing that a lot. We have now a very clear relationship between generalized Kahler and non-commutative algebraic geometry. Okay, but I'm not going to talk about that today. So we have these holomorphic Poisson structures. So then you could ask, well, okay, what about this QA and QB? Those are Poisson structures as well. Are they holomorphic? And the answer is no, they're not holomorphic. So QA and QB do not define holomorphic Poisson structures. Instead, they form what's called a holomorphic Dirac structure. So the idea of a holomorphic Dirac structure is that you should have a subbundle. You should have a subbundle D inside T plus T star should be maximal isotropic, and it should satisfy D bracket D is in D. Okay, and this is what a Dirac structure is. Okay, so for example, D could be the graph of sigma. It could be that you have a map from T star to T, and you take, if you took the graph of sigma viewed as a map from T star to T, that's one possible Dirac structure. Or you could take the graph of a two-form, okay, and the idea is that this was something discovered by Courant and Weinstein. Okay. They discovered that if you consider maximal isotropics, which are closed under this bracket, then you generalize at the same time the concept of a Poisson structure and a closed two-form. And so this D, right, if you have one of these, you could always project it down to T, and what you'll get is a subbundle of T, a distribution T. Okay, and that distribution is the one for that I drew up there. So, so this means, just summarizing this means that on each of x plus and x minus, each of these complex manifolds, we have holomorphic Courant algebroids which I'll call epsilon plus, and epsilon minus, or sorry, E plus and E minus. So this is a holomorphic version of T plus T star with the inner product and the bracket. Okay, so the only difference is that in the holomorphic category, you can't be guaranteed that exact sequence is split. And in this case, that's what happens, that the bundle gets slightly deformed. It's not the holomorphic tangent plus the holomorphic cotangent. You can start with that, but then you deform it a little bit using, you see, like in the smooth setting, what you do is you take T plus T star and then you use the 3 form in order to deform the bracket. In the holomorphic category, you take T plus T star and you use the 3 form to deform the bundle and the bracket. So both are deformed. This deformation is not available in the smooth case, but here it is. So we have holomorphic courant algebroids, each of which is equipped with a pair of holomorphic Dirac structures. So what you get is that E plus, for example, is a direct sum of 2 Dirac structures, which I'll call A and B, and these correspond to the QA and QB. And the same thing goes for the minus side. Okay. Yeah, it's exact, but this bundle is a different holomorphic bundle than T plus T star. It's not exactly the direct sum. It's like you take the direct sum as a vector bundle, and then you deform the vector bundle using the 3 form in a certain way. It's like deforming the D-bar operator on that bundle. No, so the 3 form, it enters in 2 ways. If you split this thing and you compute a 3 form like in the old case, what you're going to get is a holomorphic 3 form. But the 3 form that we had in the geometry is not a holomorphic 3 form, it's a real 3 form. So what you do is you use that 3 form in order to deform the bundle instead. And then, in principle, if you choose a splitting, then it will pop out a holomorphic 3 form in addition. No, not a holomorphic splitting, yeah. And indeed, in this case, the holomorphic splitting in general won't exist, so you won't have a holomorphic 3 form in general. It's only in a special case when that happens. Okay, so yeah, it's in.
That's represented by the 2-1 partitions.
Exactly. This is in H1 of omega 2 closed of x plus minus, and inside here we have the 1 comma, the 2 comma 1 part of H with respect to the plus or minus complex structure. That has a class in here, and that's how you obtain this class. Okay, so far we're finding more stuff, right? This is still a little bit old news, but never mind. The point is that we have 2 complex manifolds, and on each of them we have a holomorphic courant algebroid, and that holomorphic courant algebroid is split into 2 holomorphic Dirac structures, which sit in here in some way. There's no reason for A and B to be have any particular intersection with T star or anything. They're just in there, whatever. Okay. So as a result of this, okay, it turns out that this foliation, at least, we can say the foliation is holomorphic. These are holomorphic submanifolds but the leaves of A, the leaves of B, and the leaves of their intersection are all holomorphic submanifolds. And on these submanifolds, like for example, on these submanifolds, we know that there's a holomorphic Poisson structure. So on the leaf, we're going to have a holomorphic symplectic form on here. Now, when you have a Dirac structure, what you get on this leaf is not a symplectic form, and it's not even a two form. You could say that it's a two form, but it's really better to think of it as a shifted symplectic geometry object. But anyway, it's almost like what you have here is a two form that is that is degenerate, and similarly on this leaf. And then when you look at the intersection, if you take the difference between these degenerate two forms, you're going to get a non-degenerate two form on this leaf. So anyway, A and B are like precursors which combine together to make this Poisson structure of Hitchin. So these two Dirac structures, you can take their intersection. Let me not explain this in great detail, but if we take A plus intersection in the appropriate sense with B plus, you get the graph of sigma plus, and the same thing goes for minus. So we can obtain the Hitchin-Poisson structure by taking the appropriate notion of intersection of these Dirac structures. And so for a long time, I would say this was the only holomorphic structure that we really understood. This was the state of the art until a couple years ago. Yeah. Okay, and so you could ask the question, that's great. We found all this holomorphic geometry, all this holomorphic stuff on x plus and x minus, but now we're treating them as totally separate. X plus is on one side, x minus is on one side. They each have this structure, but how are they related? So the main question is, how is the holomorphic plus side related to the holomorphic minus side? And then you could also ask, what about the Kahler class? Is there a notion of Kahler class? And what about the Kahler potential function and all of that stuff, right? What do we do with this? Okay, so to describe this, we need to, okay. I don't want to say that we need to, so what I'm about to do is something that many people will find quite unpleasant. And I don't disagree. But I've come to think it's beautiful after some struggle and time on it. And it has to do with looking at this picture in a new way. So these are subbundles of this, maximal isotropic subbundles. They're Dirac structures, like I said before. And therefore, they have a bracket. They're closed under this bracket, and the bracket becomes a Lie bracket. So these are basically like sophisticated Lie algebra type things. These are basically Lie algebroids. Okay? So A plus and B plus are Lie algebroids. And because they're Lie algebroids, that means that they are the infinitesimal objects of a Lie groupoid. So let's integrate them, if possible. Okay, and so you may have to study the nature of A plus and B plus to know whether they are actually integrable to groupoids, because unlike Lie algebroids may not always be integrable, but most of the time they are. And if they're integrable, then they'll have Lie groupoids associated to them. To Lie groupoids, which I'll call GA and GB. Okay. So what is this? So now what we have is we've got. So let me just draw a picture of one of them. So GA, this is a, what is this? So this is a complex manifold. We have two maps to x plus, let's say. The dimension is equal to twice the dimension of x. So this has twice the dimension of the base space. And the point is that you should think of this thing in the following way. You should think of it as, right, and then there's a map in here, which is called the identity map, so that basically what this thing is this is a Lie group, except that instead of having a single identity element, it has an identity element for every single point in x plus. So x plus, you should think of it as being inside G plus, and it's consisting of all of the identity elements of G plus. And every other point in G plus, okay, it has a source map which produces fibers like this. These are the S fibers. And there's also the T fibers. Okay. And the point is that this point in G plus, you should think of it as having a source, which is this point, and a target, which is this point. And so you should think of it as an arrow, which goes from here to here. So this is like a Lie group. It's a smooth, complex manifold which acts on X in a certain sense, that it consists of arrows which you can think of as beginning and ending at certain points of X. And the orbits of G A plus in X plus are the leaves of A plus. That's the point. The point is that instead of just having a distribution in X, which is telling you about these foliation leaves, okay, what we want is a space that parametrizes essentially the paths. So this should be thought of as the paths, as the A plus paths up to homotopy. Okay, so these are paths that remain along the foliation of A, and GB are the paths up to homotopy which remain on the foliation of B. And anyway, so you get this thing. Yeah, I can explain, how you would use the AKS-Z construction in order to build these spaces. This was something that was elaborated after their work by Pavel Trivera, but let me not get into that.
But is it 3D?
You could think of it as a 3D topological theory with the appropriate boundary conditions to give this, yeah. Yeah.
These foliations are not the foliations of QA and QB.
Yes.
They are.
Yes.
Then how they are transverse, how these Dirac
The Dirac structures are transverse, but it doesn't mean that.
both of them are coming from Poisson, so I don't understand how they sound.
Those are real Poisson structures, and these are Dirac structures. These are holomorphic Dirac structures, which have a secret underlying real Poisson structure, but that real Poisson structure is not a holomorphic Poisson structure. It's really a Dirac structure that has a kind of Poisson-Neuenhaus type thing, whatever. Anyway, the problem is that there's members of the audience that know too much, and they're at risk of derailing my talk with their volumes of knowledge. Okay. So this means that we have on X plus, we have a groupoid of twice the dimension, okay, sitting over it.
Is this why you know these groupoids exist? Because you can take the foliation of the groupoid?
No, there's always some problem of potential lack of smoothness, whatever. I mean, you don't know that they exist. You never know that they exist unless you check. And every time I've checked, they exist. Okay, so the fact that they may not exist in some cases doesn't perturb me. That's what I'm trying to. The political view is don't be afraid of the fact that they could, in principle, in some special cases, be non-integrable. Okay, let's just assume that they both exist. So we have two of these things, giving us the foliations, the orbits of A plus and B plus. Okay. Okay, but then we ask, what does it mean? What does it mean that both of these Dirac structures, you see, like, these are not just Lie algebroids. They're present inside a Courant algebroid, and they are compatible with each other. Okay, so, for example, okay, this is maximal isotropic, and this is maximal isotropic, and they're transverse. They're like complementary to each other, right? So what does that mean? That means that if I use the inner product, then this would be identified with the dual of this. So there's a duality pairing between these. Okay? So this means that, what is this guy? This is a Lie algebroid whose dual is also a Lie algebroid, and that's what we call a Lie bialgebroid. So A plus and B plus form a Lie bialgebroid, okay, which was something that was first occurred in the study by Drinfeld on Poisson Lie groups and quantum groups. Okay, so, and this tells us something very important. It tells us actually that the bracket on B plus, it induces a structure on A plus, because A plus is the dual of B plus, and that structure means that this groupoid actually has a Poisson structure. Notice, this thing wasn't associated to a holomorphic Poisson structure. Remember, I told you there's QA. QA is real Poisson, but this QA is not holomorphic Poisson. So we integrated it, and we got this groupoid, and this groupoid is Poisson. And so that means that this groupoid can be integrated itself. We could think of the Poisson structure on that groupoid as being one of these Dirac structures. It's a Lie algebroid, and we could try to integrate it again. Right? So this is the part that you may be disgusted by. So there is a groupoid up here, and the situation is completely symmetrical. So this is also Poisson, and it can be integrated, and it has exactly the same integration. So this is what's called the double. Sorry, this type of microphone is extremely irritating. It's like quantum mechanics. You're going to destroy the state by measuring it, by recording it. This is the double symplectic groupoid. Okay, so this is the type of structure that occurs whenever you have one of these. This is sometimes called a Manin triple. And with the integration of a Manin triple is something like this. It's a double symplectic groupoid. These are what are called quasi-symplectic groupoids with Poisson structures. And this thing has a Manin triple. Okay. Let me just check time. Okay, great.
I mean, like, I can wonder what I can see as like the two outputs, right? If I integrate them all together, like the output.
Yeah.
So is that what this is just written as?
So, yes, that's the easy. If that's the easiest way to end that path, yes. The truth is yes, of course it is, yes. Yeah, the problem is that, yes, 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 that's why I prefer this instead of some weird, non-explicit infinite dimensional two-groupoid, okay? So it's actually quite important that it's appearing here in this format. Integrating the Courant algebroid abstractly would have been of no use. That was 10 years ago I knew that this was a possibility, but it led nowhere. Okay, I mean, you could prove me wrong, but yeah, but it's very important that it occurs in this way. Okay, so now we're in this world, okay, and we've got a double symplectic groupoid on this thing. And then we need to understand these things because it turns out that the relation between the plus and the minus holomorphic sides can be described as a relation between these D plus minus, these double groupoids. That's the point. Okay, so in order to understand what the relationship is between the plus and the minus side, it is the only way that I know how to do it at this point is to describe it in terms of these holomorphic symplectic double groupoids. Okay, so I just want to say a few words about these double groupoids. Okay, you could think of them. So notice that. Let me just erase the decorations here. Okay.
Sorry, can I ask as an expert, is D something universal?
Yes, everything is canonical, completely canonical. This is completely canonical, so is this, and so is this, except for one thing, which is that whenever you integrate a Lie algebra to a Lie group, if you can integrate it, there's many Lie groups that can have the same Lie algebra. They form a category. They're usually coverings of each other, like SL2 versus PGL2, right? So they can differ by topological factors. But there's going to be a simplest one and a maximum one, and there's going to be stuff in between. And that's the case for all three of these things.
Is it a two-limit?
Is it a what?
A two-limit.
No. This is new data on top of this. It's not determined by these two. It's not determined by these two. I mean, you can determine it by certain structure on top of this, but knowing this groupoid and this groupoid is not sufficient to obtain this. Because this thing has a Poisson structure that it obtains from here, and that Poisson structure is used in the construction of D.
You need more than the 4 arrows.
Correct. Yeah, that's right. Okay, so we could think of this in a certain way. So we can say that anytime you have a groupoid like this, right, you can always take the quotient of x by the action of G. You could take the quotient of x plus by the action of GB, so I'll get x plus mod GB. Okay, but this thing is a groupoid over this, and I can also take the quotient of this by that. So I could also produce the quotient GA plus mod D. Let's say, call it D plus, say. And because these groupoid structures, okay, because these maps are homomorphisms of these groupoid structures, that means that these maps descend down here, and this becomes a groupoid as well, the quotient. Okay, the only difference is that these are not smooth manifolds any longer, they're stacks. So now we have a groupoid of stacks, whatever. So this thing is a groupoid of stacks. Okay, and then you could take the quotient of that, and you could go to what you might call like that. Okay, so you can see that you get a double quotient, and what I would like to call this is a 1, 1 stack. Okay, because it's being presented to you as a double quotient from in two directions, okay? So it's not, it is a two stack. This will embed into the category of two stacks, but it is in a slightly refined category of 1, 1 stacks. Okay, and the thing is that you could have done it the other way. You could have taken this quotient first and this quotient, obtained a groupoid in stacks, and then take the quotient of that. And the idea is that those two should be thought of as canonically equivalent objects. So there's only one stack associated to a double groupoid, and it's this one, okay? And somehow, so this is sitting inside two stacks. Okay, so I'm running out of time, so what I'll do is I'll just give the answer. So I think I can say the answer. So the relation is, okay, that, let's write D minus so this is the double groupoid associated to x minus, okay? And then the one associated to x plus, actually let me put it here, so x plus okay, so we have the groupoid for x plus and we have the groupoid for x minus. And the idea is that there is no, it would be great if there was a map, let's say like a homomorphism of double groupoids from here to here that would relate the two sides, but there is none. There is no holomorphic map between x plus and x minus. However, what there is there's a space here with a which forms a span over x plus and x minus. Okay. And you see that in the way that I've drawn the diagram is that Z0 is mapping to x minus, Z0 is mapping to x plus, and A minus is a reflection of A plus, and what's happening is that these groupoids, sorry, I changed the notation from GA plus to A plus. I'm not writing the G, but these are the double groupoids, okay? So this thing is acting on X, but it's also acting on Z. And A plus is acting also on Z. And the idea is that this guy here is giving us a Morita equivalence between this and this. So you should kind of like horizontally collapse this into one object, right? So you could think of this as a single groupoid on one side, a single groupoid on the other side, and this is a bimodule where both the groupoids are acting, okay? And this is all holomorphic, including this middle stuff. And so this is what's called a vertical Morita equivalence of double groupoids. Okay. And that's not all. So this is mostly telling us that, for example, A minus and A plus are Morita equivalent. Okay. So what does that mean? That means in particular that if you look at the x minus side and you look at its A minus foliation, and if you look at the x plus side and its A plus foliation, those foliations are very tightly related to each other, and they have isomorphic leaf spaces. They really have the same leaf space. Okay? That's what this vertical Morita equivalence says. Now, it turns out that there's more data where you need to, let me just draw it here. So B plus, A plus, D plus. Okay, and here there is something like this, and there's a horizontal Morita equivalence of double groupoids. between this and this. Okay, and here's the part that really bugged me for the longest period of time, which is that it's very important that on this side, we need to take these complex manifolds, okay, and we need to convert them into their evil versions, which is their complex conjugate complex manifolds. So if we complex conjugate all of these, this will still be a holomorphic symplectic double groupoid. They're just the Galois conjugate of the first ones, okay? And that turns out to be what you have. So you have a horizontal Morita equivalence that way. Okay, but now that you have this picture here, then you could take this picture and take its complex conjugate and put it here. So that would give you just the complex conjugate of that morphism. Okay, I'll be done in a second, don't worry. And if you take the complex conjugate of this, you'll get that. And so what you end up with in the category, in the 1-1 category of double symplectic groupoids, okay, we have this diagram which is like this. So you have 4 double groupoids here, let's say here, I'm going to draw it like this. 4 double groupoids, and these 4 double groupoids are related in particular way, okay? They're related by, these are related by a vertical morphism. This is what's called a 0-1 morphism. In the 1-1 category of double symplectic groupoids, we have a vertical Morita morphism, okay? And then we have another one here, which is another 0-1 morphism. And then we also have these horizontal morphisms, which are 1-0 morphisms, like this. Okay, and so far that's what we have. Okay, now in this 1-1 category, right, you notice that what we've produced is a loop. We've produced a loop in the category of double groupoids. We have 4 double groupoids. They happen to be related by complex conjugation, but never mind. They're just 4 separate double groupoids, and we've related them by this boundary of a square. And the point is that to understand how the generalized Kahler geometry is embedded here, it's important to realize that that square is filled. It comes with a filling. So there is you could call it like this. There's a 1-1 morphism. And that 1-1 morphism is a space in the center which has maps to each of these bases such that this groupoid acts here, this groupoid acts here, this groupoid acts here, and this groupoid acts here. And just the last thing let me do is to circle what the symplectic spaces in this diagram are. So these are symplectic double groupoids. There's a symplectic form here. There's also a symplectic form here, here, and here. This is at the same level as that, so this also has a natural symplectic form, and so you could say that these 2 groupoids are symplectically Morita equivalent. Right? Similarly for this, this, and this. And then the last thing that is symplectic is this. This is the last symplectic manifold. Okay, so what I've described here, this diagram is kind of like, well, at first time that I saw it, it was more like a satanic, type of thing. I'm not usually very superstitious, but anyway, this is the holomorphic substructure of a generalized Kahler structure. That's what it is. It consists of this diagram in this category of double symplectic groupoids. And it relates the plus and the minus and the so on. And then the last thing that is needed is to understand how does the metric occur in this picture. And the way that it occurs is by specifying Lagrangian submanifolds of each of these symplectic manifolds. You have to specify a Lagrangian submanifold in a particular way, which I don't have time to go into. But just to conclude, what I think is interesting about this is that by investigating the geometry of this generalized Kahler manifold, what we're eventually seeing is we're seeing the 2,2 sigma model. We're ending up with something that involves a surface and a boundary. And this surface, it's not a coincidence that we're seeing the structure of the sigma model show up in the geometry of the target. It's just that relationship hasn't been made explicit at this point. We don't yet understand how this picture can help us to analyze the original sigma model. Okay, so I'll leave it there. Thank you for your attention. Yeah, I didn't have time for the gerb, but very quickly, the point is that that 3 form, you could think of it as a holomorphic gerb on X minus, right? And so this thing here has a gerb, okay? A holomorphic gerb. That's why there's a holomorphic Courant algebroid here, okay? And it turns out that this gerb, right, look at all these things that are acting on this space. A minus is acting, B minus is acting, and then this is acting on these. So what we want is for the gerb to have an equivariant structure with respect to A minus. The gerb here should have an equivariant structure with respect to GB plus, so that the gerb will descend here. And similarly, it has to have a GA equivariant structure. So you equip it with a GA equivariant structure. Okay, but that can be reduced down here so that the reduction of this gerb to here, this gerb, gets an equivariant structure for this. And so as a result, the gerb passes down to the quotient. Okay, so and then with this diagram, the fact that this is Morita equivalent to this means that that Morita equivalence, I can use it to transport the gerb from here to here to here to here, and the gerb remains the same. It's the same gerb in all of these different things. So basically, you see that that the correct way to pre-quantize generalized Kahler manifolds is to equip this level with gerbs, the level like 0, 0. Then level 1, 0, and 0, 1, they all get objects of gerbs. And then finally, up here, we get a line bundle. And the line bundle has a connection, and the curvature of that connection is the symplectic form here. So we get a pre-quantized symplectic 1-1 stack. Okay, and that if I was dead, I would be rolling over in my grave. But anyway, that's the reason. Yeah.
I was just wondering if, like, in specific examples, like as you said, the even dimensional Lie groups, can you identify this object somewhat explicitly?
Yeah, the cool thing is that one of the nicest examples of generalized Kahler, they occur on the group manifolds for compact semi-simple Lie groups, right? And those groups, you can construct this explicitly because it's a compact group, it has a complexification. And that complexification, you can use it to produce these holomorphic things explicitly. So you can identify, these become action groupoids in that case, and then this becomes like a double action groupoid. So you can explicitly construct everything. And then you can see like the generalized Kahler metric, how it occurs in this way. It's very strange, especially because for these groups, it's rare that we see like this, the complex conjugates are things that we never really considered as being important, but the gerb that exists here, it has this interesting kind of real structure almost, because if you have a gerb here and a gerb here, which are Morita equivalent, it's almost like you're saying that the gerb has a real structure, since this is the complex conjugate of this. So yeah, it's interesting that these groups have this structure.
So usually to construct pre-quantization, you need some integrality conditions.
Yeah. So everything that I said here, this is just a double symplectic groupoid. It has a symplectic form, but there's no guarantee that that would be pre-quantizable, that there would be an actual line bundle with a holomorphic connection whose curvature is this holomorphic two form. So there are obvious pre-quantization conditions throughout this whole diagram. Yeah. Yeah. Yeah, so the way that we're constructing this in the paper that we're writing with Yusong and Daniel is that we take advantage of the fact that we know that these complex manifolds are really coexisting on the same smooth manifold. And on that smooth manifold, we have all of the tensor fields coming from generalized Kahler geometry. So we have tons of tensor fields, right? And some of those tensor fields, you can view them as, you can literally view some of the tensor fields as Mohr-Cartan elements, okay? So for example, I'm not going to be able to say it exactly correctly, but for example, this groupoid, okay, this groupoid, it has a deformation theory. It has a deformation theory, which you can deform it as a bimodule over itself, because the groupoid is a bimodule over itself, right? So if you think of it as a bimodule, instead of thinking of it as a groupoid, you can try to deform it as a bimodule. And if you deform it as a bimodule, you can describe the deformation elements as Mohr-Cartan elements. And the amazing thing is that some of those generalized Kahler tensors, they are the Mohr-Cartan element. So they give you a deformation of this to this. And then you could see even that you can deform from this even to this. And you can see that this one is kind of like halfway in between, something like that. So there's a way of doing it by deformation theory. But we're taking assuming that we choose this, if we choose this integration, this one, because there's always this choice, like there's always this choice, this categorical choice of which integration you're picking. Okay, but once you pick that, then this is canonical, and this is canonical. So this choice determines this choice, and it determines this choice, and so on. So there's some kind of choice of like a Lie group or like a topological choice that you make for this guy, and then it transfers over to the rest of the diagram, and then the rest of it is there's no choice. It's kind of funny because you're kind of led to the idea that maybe the physical theory, in order for the physical theory to be defined, maybe what you need is for this to be pre-quantizable and for all these choices to be made. And maybe that is part of the definition of the 2,2 sigma model, because there's some kind of topological thing that needs to be chosen. But we haven't really gotten to that point of understanding those choices very well. Yeah, so for example here, like if you look at all the symplectic spaces that I've circled, okay, this one is a double groupoid, so it has an identity bisection here for this, and it has an identity bisection here. Both those identity bisections are Lagrangian. So this guy has two holomorphic Lagrangian submanifolds for free. You don't have to choose anything. Okay? So does this, and this. This guy, however, it's only a groupoid in one way, and it's lost its other two legs. The other two legs, which used to be a groupoid, now they're like mapping here and here. So this only has one groupoid structure. So it only has one holomorphic Lagrangian for free. And this guy also has one, and this has one, and this has one, okay? But what you're supposed to do in order to get the metric is that you're supposed to complete the choices So you're supposed to complete the choices by choosing a second Lagrangian here, which doesn't have to be holomorphic. It can be C infinity Lagrangian. And then you need to choose one here, right? And those two choices of smooth Lagrangian submanifolds, they filter through to the rest of the diagram, and they make sure that all of these symplectic things all have a pair of Lagrangian, real Lagrangian submanifolds. Those Lagrangian submanifolds, those real Lagrangian submanifolds, they deform by a function. That generating function is the Kahler potential, okay? But there is something slightly unexpected, which is that what we're finding is that there are two functions. There are two functions and not one. And I can say a little bit about how that, because you might think that that invalidates or is against some of the things that are written in your papers. But I think that it's still consistent because when you look in special cases, the two functions can coincide, or they can be like, it becomes one degree of freedom in certain cases if you assume that certain fields are not present. But if all the fields are present, like the twisted chirals and the chiral and anti-chiral, if they're all present at the same time, what it looks like to us is that you need two functions to describe this function. This. No, in the regular case, it turns out that the two that they do determine each other, that they coincide. Yeah, yeah.
The one case which physicists would be like the hypergalactic biology, not necessarily hypergalactic transverse.
Yeah, I mean, there's a couple of special cases, like the commuting case, right? And in that case, the two choices of function collapse for a different reason, and for the case that is full rank, then they coincide for a different reason. It's very strange. I don't quite understand, but yeah. But it looks like in general there would be two degrees of freedom, and they're not independent. They have a slight constraint. So anyway, it's kind of annoying. Yeah. So in order to work locally, you need to choose a point, and these have Lagrangians, so you can map that point over. There's going to be a single smooth point, and then you could work in a neighborhood, all small arrows. You just take small arrows in all these groupoids. If they're sufficiently small, then everything's local, yeah. If you split the coordinates into if you split it into a product, then you can argue that on one side they coincide and on the other side they coincide. Yeah. 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 Yeah, so do I. I would say I know that it is, and that's what I just told you, yes?
There's a notion of frequentization for
Yeah. Yes, yes. Yeah, it's the same. It's the same, yeah. It's just that this one we have a full description of what it is, plus more. We have the Hermitian structure. Remember that this is the holomorphic picture, but then there's something that goes beyond the holomorphic picture, which is the choice of a Hermitian structure. So you have not only this holomorphic prequantization, but you also have a Hermitian prequantization. And so we see all of that stuck in here. So yeah, it is helpful that that these shifted symplectic language is available, but yeah. So we're intersecting with a certain amount of that stuff, finding examples of where they actually occur. Yeah.
Okay, thank you very much, Mark.
Okay, thanks.